Okay, week 10. Week 10. There's only 12 weeks in semester. Hoo-wee. All right, so what you're being dumped with this week is assignment 2. Assignment 2 is about writing a software agent to play some kind of simple gamey type thing. Basically, it's something that simulates a truck that drives around a ring road, picking up stuff, buying stuff, picking it up, and then taking it somewhere else and selling it at a profit. So that's the plan. It's due on May the 31st. What's the date today? It's the 8th. Oh, there you go. You've got lots of time, 23 days. It will involve tournaments, so your bot playing against someone else's bot, and those tournaments are going to start on May the 16th, so make sure you've got something, at least something simple running by then. So, I mean, part of the deal, as soon as you say bot or software agent or whatever, there's some kind of notion of intelligence. In this case, it can be very simple. It can just say, go to the next location, whatever's there, buy some of that, and then go to a place where I can sell it. So submit as soon as you've got stuff. Now, I don't know what Andrew did in Assignment 1. He might have had a Git backend, but basically you use give. Give will put something into GitLab, and so there's a track of what you've done. Now, if you magically come along in the last day and that's the only submission you make, that's a little bit sus or a bit annoying anyway. So the idea is that as you work, you submit partial solutions whenever they're ready. So you do some work, submit using give. Do some more work, submit. Do some more work, submit. Do some more work. And when I say do some work, at least a couple of hours of modifying stuff would be the kind of level. Don't submit after every semicolon change. And the reason we want you to do that is we're trying to track you, keep a track of how you work on the assignment. So just to make sure that you start early. And I bet if I was to go and check the blogs that said, if I go back 4 weeks, what would I have done differently with assignment 1? How many people said I would have started earlier? There's 2 honest people in the room. 3, 4, yes. I bet just about everyone would have said that. So never leave software stuff to the last minute because you'll never get it working. Of course, leaving it to the last minute is a good way to practice for exams. Although it's an order of magnitude more difficult what you're working on. The bot that you have to write doesn't have to be an entire program. It's just something that's going to make strategic decisions about playing the game. There's going to be a driver program, which Andrew's called a referee, that will invoke your bot and then do whatever your bot tells it. So, hey bot, what do you want to do now? And you send back a command and the driver program goes around and changes the state of the world appropriately. This week we're going to talk about some of the data structures in tutes, and there's going to be a little bit of stuff in the lab exercises. So the plan is that you should read that file before the tute. If your tute happens to be at 1 p.m. today, you'll have to read fast, or you can read while I'm talking. So why are we doing assignment 2? Because software agents are a hot topic. You need to eventually learn how to manipulate complex data structures. And when I say complex, they're not super complex. There'll be a list of places. Each place will have certain properties. The bot itself will have certain properties, like how much stuff it's carrying, what stuff it's carrying. So all that's going to be represented by a bunch of linked structs. Okay, so the kind of stuff we've been talking about for the last couple of weeks. Eventually, just about every program that you write is going to be going to involve a bunch of linked structs. So it's useful to learn how to work with them now. And similarly, practicing with pointers is also important because you've got an exam on manipulating pointer-based data structures in week 13. Any questions on that? Good, because you probably haven't read anything on the spec yet, so you can't ask questions. All right, so today the deal is we're going to talk about abstract data types and then a particular instance of an abstract data type, which is a stack. All right, before we talk about abstract data types, what are data types? Basically, a data type is a collection of values and a collection of operations that manipulate values of that type. So you've seen plenty of examples already. Integers, you know what the values of integers look like. They're written as digit sequences, maybe with a minus in front. And there's a bunch of operations which are written as operators in the C language. Similarly for char, which is, when it gets down to it, is really just a variation on int, but the values look different. They've got single quotes around them and they've got a single character in between, various kinds of characters. There are also operations that you can perform on char values. You can actually add them together, or you can add a constant value to a char, or you can subtract two char values, which you might have seen if you've ever implemented something to take a sequence of digits and turn it into a number. And there are various library functions that are also available for char values from one of the C libraries. Then last week we looked at lists, so the values that lists have, a sequence of values of some type. We were just dealing with integer lists. So lists of integer values that can look like that. When you display them, you can't feed them into the program in that format there without doing some reading and parsing and so on. And the kind of operations that we had on lists, inserting into a list, deleting a value from a list, working out its length, and so on. So these are the common characteristics of data types, a set of values and operations that work on values of the data type. All right, so what are abstract data types? Well, they're really just a technique or a style, if you want, for defining data types, defining new data types. Two of those data types that I mentioned above, int and char, are already defined in the C language, so they're predefined. Lists, we defined a simple list data type last time. Abstract data types are basically ones where what you show to a user of the type, so there's this notion of the person who implements the data type and there's the person who's using the data type. What the user sees is a very restricted view of the data type, and typically for any kind of structured data type, all they see is a pointer. So we give you a pointer and say, hey, this is pointing to an object of a certain type. You don't have to worry about how the object's represented, what it looks like internally, doesn't matter. Just take this pointer and treat that as an object of the type, and then if you want to manipulate that object, here's a bunch of functions that you can use to manipulate that particular object. So what the user gets to see is an interface, basically the operations of the type plus a pointer. What the implementer has to deal with is real data structures that produce a representation of the type. Now for lists we saw something like struct node, and what we gave to the user who was manipulating the list was a pointer to the first node in the list. They didn't actually have to know what a node looked like in its entirety. All they had to worry about was, here I've got a pointer, and using that pointer I can do whatever I like with this list. I can add things into it, I can check whether things exist in it, I can remove things from it. So we implemented the struct node and all of the functions that worked on struct nodes and linked collections of struct nodes. So what a user sees is an interface which is a pointer and a collection of function signatures. That's the type as far as they're concerned. As implementers, what we have to do is build a type, a representation of that type, and implement operations on that representation that satisfy the semantics of the operation. So when you define operations, as well as giving an interface, there's a notion that you're saying what this operation is supposed to do. So if I, for example, insert operations on lists, I can say, if I take a list and I take a value and I do insert that value in that list, then I'm going to get a new list, which is like the original list, that has everything that was in the original list, plus it has the new value at the start of the list. And we could try and write that formally if we wanted to. So that's the semantics of the insert operation, and then we have to come up with an implementation for that. Right, so when you're implementing abstract data types in C, now plenty of languages implement abstract data types, and a lot of languages support abstract data types better than what C does. So C is an ancient language, but it's a really nice language to start with because it's so simple to get into. But a standard way of implementing abstract data types in C is to have a .h file, which is the interface, and that's what you give to the user, and the user does a hash include of that. Now we saw that last time, hash include list.h, and we've seen it plenty of times, hash include standard.io.h. And standard.io.h with file stars is absolutely an implementation of an abstract data type. So you want to be able to manipulate files, you want to open them, give them their name, you want to scan through them, do fgets, read a line from a file, all those kind of operations you do, you're given a file star, so you're given a pointer to an object. You've got no idea what that object looks like, unless you go and read standard.io.h, but you're perfectly happy to use it. So here's this file object, I can set one up by doing an fopen, I can do fgets, I can do fclose, I can do fscanf, and so on. So all I get to see is the pointer and a bunch of operations which are written up in the Unix programmer's manual. And given that information, I can then go ahead and I can use files. So in C, what we give to the user is a .h file that defines what are the operations on this type, essentially. There's also, sitting in the background, there's a .c file, which is what we as implementers have to build, and that .c file will be compiled and it will sit there in a library, and when we do the final compilation of the user's program, we'll take the user program, we'll take our library, and we'll put them together, and that will give the final executable. Now, a lot of the time that's invisible because things like standard.io and standard.lib are so important that we always include those libraries in the final compilation step. So we don't actually see that. It kind of doesn't show up anywhere. But if you, for example, if you start using mathematical functions, then you'll pretty quickly find that you have to mention that you want to use the maths library. And you do that by saying on the final compilation line, you have to put -lm to include the maths library. As I said, things like standard.io and standard.lib are so important that they're always included without having to be explicitly referenced. If you're writing your own data types, then you're typically going to provide a .o file, and the user will link the .o file with their main program that makes use of the data type and produce a final executable. All they get to see is the .o file. They don't actually see how the objects are represented. So one very important thing is that the user can't fiddle with the internals of the object. All I can do is take the object, point it to the object, and invoke the whatever functions you define and make available to them. All right, so Types in this context are defined essentially as pointers, and they basically give you a reference to a data structure, and as a user of the type, you have no idea what's in that data structure. Like you have no idea what's in the type at the end of a file star, and you don't need to. So users manipulate objects of the type using the definitions of the interface, and I've already said that file star is an example. So your average ADT has a number of operations on it. Usually there's an operation to create an initial instance of an object of that type. So creating a list creates an empty list. We saw there was an operation to free a list. So you could call that destroy if you wanted to. Basically frees up all the memory that the object was using. And typically there'll be a function to display the current value of an object of that type. And then because these abstract data types typically represent collections, although not always, but most of the time they do, you'll have operations to insert values into the collection, operations to remove values from the collection, find values within the collection. You know, if the ADT was representing a set, then is this a value a member of the set, that kind of thing, and the size of the operation would be typically available as well. Like if you're talking about sets, there might be an operation to get the cardinality of the set. Alright, so that's a bit of background for ADTs. We're going to look at a specific ADT, which is stacks. So stacks are basically a collection data structure, a linear collection like the linked lists we looked at last time, but they have a particular way that you're supposed to access them. So you can put things into the list and you can take an item out of the list, but you always take out of the list the last item that you put in. It's the only way you can manipulate the list. Put an item in, pull an item out, or pop, that's what the function's called, and that always takes out the last thing that you put in. So basically that's what defines a stack. The semantics of those two operations tells you what a stack's like. Conceptually, you can think of a stack as a pile of plates or whatever. You can pile up the plates. If you want to take a plate out of the pile of plates, you don't tend to pull the bottom one out, because otherwise the whole thing falls over and you break all your plates. You tend to take them off in the order that you put them onto the list. So the last thing you put on is the first one that you take off. In some senses, stacks are just a variant of the list data structure that we looked at last time. The only way of putting values into the stack is to use the insert operation, and the only way to do a delete is to delete the element at the head of the list and grab its value at the same time. So why do we care about stacks? Because they're really a really important data structure used everywhere. There's only two examples there, but C function calls are done using a stack. Not necessarily a stack ADT, that's slightly different, but stacks end up being used everywhere. Another very common application is to match things. And the example that we'll look at now is bracket matching. Okay? So we want to scan through a program, and this is something that the C compiler does. It'll tell you if you put in an opening brace and forget to put in the corresponding closing brace. So let's take a look at a client program that uses stack, and then we'll actually go and implement the stack in a number of different ways. That was something else I should have said about ADTs. ADTs are nice because all that the user sees is a pointer and a bunch of functions. What's sitting behind they got no idea about. So you as an implementer can change the back end as much as you like. And if you implement, let's talk about a stack, you implement a stack one way and that turns out to be inefficient or not effective, you can go and change the stack. The user doesn't have to change their programs that use a stack, because all they see is the functions. As long as you don't change the interface, then the user's program is going to keep working, but it might work better because your new implementation is better. Alright, so let's have a look at the problem of bracket matching. So here's an imaginary C program. It's actually not very realistic because the C program wouldn't start with a parenthesis. It's more likely to start with a brace. But in any case, so we've got a sequence of these brackets and we want to make sure they all match. So if we see an opening square bracket, we ought to see a closing square bracket. If we see an opening brace, we eventually should see a closing brace. If we see an opening parenthesis, eventually we've got to see a closing parenthesis. If we see an opening square bracket, closing square bracket, and eventually, if we scan through this whole program, we should see the final closing bracket matches the initial bracket that we first saw, and if that happens, then everything, and if everything in between matches, then we're happy with the way the brackets are set up. So we can implement the check for that using a stack, and the reason we need a stack is, if we're somewhere in here in the middle and we see this thing, we want to make sure that the most recent bracket that we added, that we saw, was an opening square bracket. So if we see a closing square bracket, we want to make sure that the most recent thing was an opening square bracket. If we see a parenthesis, we want to make sure that there's a corresponding opening parenthesis. Now, because we've got these square brackets in between these parentheses, we want to make sure that once we match these things, we throw them away and we're not interested in them anymore. So the way we can implement that is using these two operations here. Basically, as soon as you see an opening bracket, you use a stack, and as soon as you see an opening bracket, you push it onto the stack. Okay, and then you advance through the program, blah, blah, blah. You imagine that you're reading, and you see another opening bracket of a different type, and you push it onto the stack. You keep looking through the input file, and eventually you see a closing bracket. Right, so what you do at this point, you take this off and check whether it matches that. And if it does, the most recent bracket that we opened was a square bracket. The bracket that we're just closing is a square bracket, therefore we have a match. So if the thing on the top of the stack, which we pop off at this point, so we remove it and we compare it to that, make sure it's the corresponding closing bracket, then we're done. And we keep scanning. We see an opening bracket here of a different type, so we add that onto the stack. The next bracket we come across is a closing bracket, so we pop that and we compare it to that and make sure that it's the corresponding bracket type, and they're both braces, so that's okay. So we pop that. The next thing we see, the next bracket we see in the program is a parenthesis, so we push that onto the stack, an opening parenthesis. Next bracket we see is an opening square bracket, push that onto the stack, keep scanning. Next thing we see is a closing parenthesis, so we pop the top element off the stack and we compare it to that, and if they're a matching pair, then we're happy. If they're not a matching pair, then we don't have a matching bracket, so we're going to print some kind of fail message. We go on to the next parenthesis, to the next closing bracket. Okay, so that the next bracket we saw is a closing bracket, so that means pop off the top element in the stack and make sure that it matches that. Yes, they're both parentheses, so we're happy there. Go on to the next bracket, happens to be a closing parenthesis, so we do a pop and compare, and if they match, then we're happy. And at this point, we reach the end of the input, and at the end of the input, if everything's matched, then we'd expect the stack to be empty at this point. Okay, so that's it. So that's the overall method for bracket matching. All right, how do we implement that in C? It's pretty straightforward. So here's a little bracket matcher. We've got a special fail function which we're going to use to give up when certain problems occur. Main program, we've got a current input character, so we're going to scan the input character by character, and we've got a stack. And that stack is going to be a stack of brackets. All right, I mentioned before the typical, so this is an abstract data type. We don't know how a stack's implemented. So the first thing we do with it is we create an empty stack. And then we start reading. And as soon as we see any kind of parenthesis or any kind of bracket, we push it onto the stack. So that's what we saw with the diagram before. As soon as we see a closing parenthesis, we want to remove it from the stack. We want to remove the top element of the stack and check whether it's a match. So if we see a closing parenthesis, then the top thing on the stack ought to be an opening parenthesis. So that's what we're checking there. Pop the top element off, remove it, and then use it to check that it's a match. And if it's not, then we get a fail. If it's a square bracket, a closing square bracket that we see, we want the top element on the stack to be an opening square bracket, so we pop it off and do a comparison. And if it is, then we're happy, otherwise we fail. And if the character that we see is a closing brace, then we expect the top element on the stack to be an opening brace, so we pop it off and make sure that it is, and if it's not, then we fail. Now, one thing that could happen in this scheme is that, I might as well just, and finally, once we finish scanning, so when we reach the end of the while loop, as I said before, we expect the stack to be empty. So we just check that to make sure there aren't too many open parentheses and not enough closed parentheses to match that. Now, another thing that can go wrong, which is kind of hidden in the code here, is that we reach a point. Let's go back to the diagram and change the parentheses. Let's imagine that the first thing we actually see is a closed parenthesis. All right? So the stack starts out as empty. The first thing we see is a close. Now, when we see a closing bracket, we go to pop and we want to check that the thing on the top of the stack is an opening bracket of the same type, so an opening parenthesis. Well, if we go to the stack is currently empty. We start out empty, so it's possible that when we try to do one of these pops, it fails because the stack is empty, and what that means is basically that we've got too many closing parentheses. Right, so two different conditions. If you've got too many closing parentheses, then you're going to bump into an empty stack partway through scanning the input. If you've got too many opening parentheses, then the stack is not going to be empty once you reach the end of the input. So let's say, all right, let's make that a brace and let's take that away. So if we did this scan, what we'd end up with when we reach the end of the input is the stack would contain a single brace. You know, as we were scanning, sure, we would have pushed that onto the stack, and then when we saw this one, we would have popped it and checked, and we would have been happy, and we would have kept going, push something on, pop off the corresponding closing bracket. But when we get to the end, we haven't found a closing brace to match with the thing on the stack, and essentially what that means is there are too many opening brackets. So that's the reason for that check down here. And the thing about having too many closing parentheses, we go to do a pop and the stack will be empty, then the pop operation is going to fail. You can't pop off an empty stack. So that's one thing I should have said before. If you want to get down to the fine details of the semantics of pop. Push, you add an element on top of the stack. Pop, you take the top element off the stack. What happens if there isn't a top element? Then pop fails. Alright, so we're going to get a failure either way. If it's a non-matching parenthesis or a non-matching bracket, we'll get a fail, and if there's nothing to pop, we'll get a fail as well. Alright, so let's compile that up. And test it out. And I've just remembered something. Let's try something really easy. And you can put whatever junk you like in between, because anything that's not a bracket of some sort just gets ignored. Okay, if you look at the code. Yeah. Right, so this should be okay, and we should have all matching brackets. Oh dear, we have a mismatch. Why do we have a mismatch? We have a mismatch because I haven't actually implemented the stack data type yet. Do that in a minute. But here's a version that does work. Let's make something that looks like a C program. Right, so we've got a few parentheses floating around in that. They all seem to match up. So that should work. Right, and this is classic Unix style. If everything matches right, it doesn't say anything. It only says something if there's a problem. Let's try some more examples. Let's say that we've got too many opening parentheses. So it doesn't matter how many lines I type, it's just reading till the end of input, so I'm just typing in single lines. Okay, so what happened there, it got to the end of the file and discovered there was still something on the stack, so we didn't have enough closing parentheses. This case I haven't actually tried, so I'll be interested to see what happens. Let's try that. So here we've got too many closing brackets. And so we're going to get a pop that eventually fails because we'll push that onto the stack, push that onto the stack, and we'll pop that one, match it with that, pop that one, match it with that. And then we'll see this closing one and we'll try to pop something else off the stack. And, okay, so we get an error pop of empty stack. So maybe what I should have done in the code to make this a little bit more sensible is in each of these cases, and one thing that's slightly annoying about this is all these cases are almost identical, so you kind of think, is there a way that I can somehow factor that out? So if the stack is empty at this point, we can at least say what kind of brackets it failed on by doing something like that. And we could do that for all of the cases. Well, I can't be bothered typing it in for the brackets, but let's see. Oh damn, I can't make because I haven't got a stack. Oh, anyway, we can test that out later once we've got a stack. Alright, so speaking of stacks, let's go back and have a look here. Alright, so we had a hash include of stack.h. So basically what that did, it told the bracket matching program, I have this object of type stacked underscore t, and there are various operations that I can do on that stack, like create, push, pop, and is empty. It's empty. Okay, so it's telling the main program that those operations exist and how it can use them. So let's have a look at stack.h. Okay, so this is a really minimalist .h file. So first thing to notice is that stack t is defined to be a pointer to some kind of struct. Here, we got no idea what that struct is. We know it's a thing called a struct stack, but we don't know what kind of structure it is, what values it contains, and so on. So the type called stack underscore t is a pointer to one of these stack structures. Is basically what that's doing for us. Oh, I didn't check that all of these were going to overflow. That's why it looks so messy. Alright, so in any case, so the create operation, we don't need to supply any input. It gives us back a stack, and it creates a new empty stack we could have put here. Destroying takes an existing stack and frees up the space that was allocated to it. Push takes a stack and an integer value, which we can call an item if we like, and it adds that onto the top of the stack. Pop takes a stack, removes the item off the top of the stack, and returns it for us to do something with it. Is empty takes a stack and checks whether it's empty, and in this case returns effectively a Boolean result, true or false. The stack is empty or it's not. The top function is kind of like pop, except it just gives you a look at what's on the top of the stack without removing it. That's not the first. Push and pop are the characteristic operations of stacks, but you can add whatever additional operations you think might be useful. So top is potentially useful. How many elements are on the stack? We can get that, and we can display the contents of a stack if we want. All right, so that's the interface, and that's what a user of the type sees. Now, as soon as you start looking around at .h files on Unix, you're going to discover that they all start with something weird like this. And down the bottom, right, so what's the point of that? They've all got it, and as soon as we start giving you .h files in the future, they're all going to have stuff like this, and in fact, TraderBot.h, I think, has exactly that. Right, what this is for, it's allowing for the fact that programs, to some extent, willy-nilly, hash include .h files. And some of the .h files they include might include other .h files. And if you're not careful, you'll end up hash including a file twice, and if you do that, you'll end up with multiply defined symbol errors from the C compiler. Okay, so let's just make. Oh, I wanted a new file. How do I get new file? Cancel. So imagine I've got x.c, which has hash include and then whatever else x.c has. And then imagine I've got an implementation of a.h called a.c, and these a things happen to use b things. So inside a.c, I hash include b.h. And then I do whatever else a.c does, and then I've got b.c, which, well, hash includes b.h, but that's okay. So actually I should have been a bit more specific. Let's say that that's a stack. Let's say that stacks happen to use lists. And let's say this is our main program, so I'll just call it main.c. Right, if I do things like that, then as soon as I try to compile main.c, the way hash includes work is that it's going to do a hash include of stack.h. Ooh, and that doesn't really prove anything what I've written there. Let's say stack. So the stack data type happens to make use of lists. Okay, so stack.h will hash include list.h. Makes perfect sense. So the C compiler hash includes stack.h, which includes all of the stack functions, but it also hash includes list.h because let's say for the sake of argument that the stack is implemented using a list. Okay? So we need to include all the list functions as well. So that's fine, stack.h, hash include list.h, no problem. But then the main program, as well as using stacks, it also uses lists. And it does a hash include of list.h, but we've already hash included that as part of stack.h. That's a problem. Because the C compiler is going to say, hey, wait a minute, you're telling me about all these functions, but you've already told me about them. Why are you telling me about them twice? Okay. So, because you can't tell exactly in what context a lot of .h files are going to be used, you want to protect against them accidentally being included twice. And the standard technique for doing that is to use another feature of the C preprocessor, which is what hash include is all about, is to use this. So basically this is saying if this symbol here, stack underscore h, and you can call it whatever you like as long as it's unique. So calling it stack underscore h in a file called stack.h is a very common practice. If I've never seen this symbol before, then what that means is I've never hash included this file before. And the first thing I'm going to do is I'm going to define that symbol. So if anybody else ever hash includes this file, they will have seen this symbol, and this hash if ndef up here will fail, and they won't try to hash include stack.h again. Okay? So what this means is basically saying if this particular name here has never been defined before, then continue and do all of this, include all of this. The first thing that you include is a hash define of that very symbol. So if I come along subsequently in a context like this, and I do a second hash include of stack.h or list.h or whatever, then when I do the hash include, it's going to look here and say, hey, stack underscore h has already been defined, so I don't need to include all this stuff again. think that was a bit of a crap explanation, but you're going to see those things quite frequently, okay? So basically, they're just there to protect against multiple hash includes happening accidentally. So when you see it, don't be surprised. All right, so where were we? Oh yeah, all right, so this is the interface that a user of the stack data type sees. That's fine, you can't run a program based just on an interface. You need an implementation, and so we'll take a look at the implementation of stacks after the break. So let's have a few minutes break and then talk about how you actually implement stacks.